too long.
It makes sense.
It's hard to upload, yeah.
It's all good. So, with t is equal to 5 seconds, we can go ahead and first we're going to find how far we went up the incline. So we're going to use x final is equal to x initial plus the initial velocity times time plus 1/2 at squared. Hopefully we remember the kinematics equation, because guess what, it's not going away. So we're going to define our initial starting position to be 0, and I'm also going to say that we start from rest. So we can rewrite this, because these first two terms go to 0, that the final displacement here is equal to 0 plus 0 times 5 plus 1/2 times the acceleration of 5.34 meters per second squared times 5 seconds squared. That should give us our displacement, or distance that we've traveled up the incline, to be 66.8 meters. Okay, so which we will define as d for the rest of the problem. So now we need to find the work that each of these, each force is doing. So we know that work is equal to force times distance, the magnitudes of both, times cosine theta, where theta is measured from where the motion is going to. So if we write work done by the normal force is equal to the force done by the normal force times the distance. Well, the force, the normal force, we calculated 144.3. So we get 144.3 times 66.8 meters. 8 meters times cosine. Wow, he's leaving the angle intentionally blank for now. It's like he's going to go back and talk about it. Huh, that's weird. So force of gravity is equal to mass times gravity, so 98, times the distance of 66.8 meters times cosine. Work done by the applied force is going to be 150 times 66.8 meters. That's also newtons. Times cosine. And the work done by the frictional force is going to be 7.2 newtons times 66.8 cosine. Cool. Now let's figure out what these angles are. And this morning, I made a mistake, and I did the angles incorrectly. So if you're watching this and you were in the morning recitation, I eventually got it right before everyone left, which is good. But you'll notice, I remember I struggled for a few minutes because I was like, well, is this supposed to be a certain way? This is the most surefire way to figure out what the angles are, especially when you're dealing with something like incline plane problem. Start here. This is our plus x axis, right? This is the incline, and it's moving up. It's going this way. So first thing is I need to find what the theta is for the normal force. That's a quarter of a circle. So because this is a quarter of a circle, because from the x to where normal is, that's 90 degrees. So because that's 90 degrees, we can put 90 in over here. Force of gravity goes from here to here. So it goes half the circle plus a little bit extra. So we know it's 180 plus this angle between the negative x and where gravity is. Well, we know what this is because we know that this is 45. Since this whole section, this quarter circle has to be 90, and this part of the quarter circle is 45, 90 minus 45 is 45. If this were 50, this would be 40. If this were 89, this would be 1. So 180 plus 45 should be 225. So it's 225 goes here. So applied force, we can do it in two ways. First, we can go all the way around here, and we can say 360 minus 30 is 330 degrees. Or we can say negative 30. We can go clockwise and say it's negative 30. Either way, I'm going to use negative 30 because it makes more sense to me. But you should get the same answer no matter which one you plug in. And frictional force is 180 degrees, half the circle. And that makes sense because we should be getting negative 1 from that. So you plug everything in to your equations here, and we get the normal force, the work done by the normal force is 0, which makes sense because cosine of 90 is 0. The work done by the gravitational force is 98 times 66.8 times cosine of 225, which you plug that into your calculator. 98 times 66.8 times cosine of 225. We get a large number. We should get negative 4,629 joules. Work done by the applied force is equal to 150 times, and we get, make sure we never get the negative there, 150 times 66.8 times cosine of negative 30. We should get positive 8,677.6 joules. And the work done by the frictional force is going to be 7.2 times 66.8 cosine of 180. So we should get negative 480. We should call it that. So that's D. We have completed D. We've done the forces. E, which I'll put here because it's the only place to put them. E asks us to prove that the total work done by the entire system, meaning the sum of these works that we calculated, is equal to the change of kinetic energy of the system. So the first thing is I need to get a total work. Well, it's equal to the sum of all of these works, right? So I'm going to take 8,677.6 minus 4,629 minus 481, and we should get 3,567.6. So 3,567.6 joules, which is the total work done on the system. So now we need to prove that this is also the change of kinetic energy of the system. So the change of kinetic energy of the system is going to be 1/2 mass times velocity final squared minus velocity initial squared. Okay. Well, I need to get the final velocity. We need this to calculate the change of kinetic energy. So we know that velocity squared, or the final velocity, from definition of acceleration, which is the kinematics equation that I hope you still remember, is the final velocity is equal to the initial velocity plus the acceleration times time. In this case, it's going to be 5.34 meters per second squared times 5 seconds. And we should get 5.34 times 5 is 26.7 meters per second, which is our final velocity, which we'll plug into this equation, our change of kinetic energy. So we get this to be 1/2 times the mass, which is 10 kilograms, times 26.7 meters per second squared minus 0 squared, which is 0. We do all of these calculations and we see if I'm right or wrong. It turns out that within a rounding error, I am correct. I get this to be 3564.45, which is, it's 3 joules off from the total work done. And And that's just because the rounding that I chose to do. If the rounding were a little bit different, it would be I would have gotten these exact numbers. Like this morning, I got exact numbers. It's just that I may have just done the rounding a little bit worse than I was supposed to. But if you follow sig figs, usually these rounding errors don't really play out. So, any questions?
Yeah. So how did you calculate work total again?
Yeah, work total is just the sum of all the individual works. So like I added, so I had 0 plus negative 4629, which is the work done by gravity, plus 8677.6, which is the work done by the applied force, plus negative 481, which is the work done by the frictional force. All that together gets me my total work. So total work is just like, it's like net work. You can think about it like that. Then you sum up all the individual works, and you should get a total number.
Okay. Can you say again what your? So you just added all the works together, you said?
Yeah.
Okay.
And that includes with the negative sign. So if there's a negative sign, I subtracted it.
Yeah. So wouldn't that be? You got 3,567. So you did 400 or 4,629 plus 8,677.6 minus 481.
Make sure that you had the 4629 as a negative sign. Yeah.